All right. So thank you everyone for joining. I'll take this point to begin the main presentation. If you haven't met me before, my name is William Ward. I'm the New South Wales Manager at Papworth Construction Testing Equipment. And what we'll be doing today is a discussion of cover meter operation and some of the new functionality on specifically Screening Eagle Technologies Proceq Profile Meter PM8000 cover meter. Practically, the first half is going to be good for anyone who uses particularly an eddy current cover meter in their work. That's a particular detection technology with strengths and weaknesses. It'll also be a useful guide on how to think about precision of measurements with a tool like that, because if I'll stress anything about non-destructive testing tools, they're not like taking a ruler out and taking a measurement. It's important to have an understanding of the operation principles of the device. That's why I start every presentation, even like this one where I'm going fairly quickly, with a little bit of theory, because if you know the theory and you've got a mental model of how the device works, you'll be better able to understand what it can and can't do and the best way to deploy it for your requirements. So after I've done the theory and the operation of eddy current cover meters, we'll be doing a specific demonstration of the upgraded functionality of the PM8000 Lite and the PM8000 Pro, along with a step-by-step tour through all of the basic settings and operation tools for the PM8000. I'll jump straight into the slide presentation. As I said, the basic format is going to begin with theory and a mental model of what an eddy current cover meter is. Then we'll be going through physical operation on site, and the detailed application of the tool. Now, Cigar, if you are looking at capabilities and accuracy, the full specifications will be in the document sent at the end, but we're going to discuss accuracy in terms of how to apply the current cover meter right away. So, should now have my main presentation visible. I'll begin going through that. Now, I can't check your chats quite as often now that I'm presenting the main content, so please bear with me as I do so. Okay, so what are we talking about is a eddy current cover meter. That's specifically going to be a tool where we are using electromagnetic energy to detect the presence of metal. We produce an electromagnetic field from the base of the cover meter, and any metallic object, principally reinforcing steel, will respond to that signal. We can determine the response by its strength and its position relative to, in the PM8000, multiple coils, to tell us the depth of a reinforcing bar and the position of that bar. If we want to do something like track orientation, we'll need to physically move the cover meter to see how it changes with motion, but we're using that pulsed eddy current to determine principally a very precise depth. In terms of the accuracy of that depth, an eddy current cover meter or a tool which is called cover meter and provided in its specifications with a record of accuracy, that is going to be your most precise tool for measuring cover depth for quality control. For example, the PM8000 out to the 60mm mark is going to be around a 1mm precision, bouncing out to 2 or 3mm at the very broadest range of its full operational depth, which is 180mm. So, and you'll find that's the same on similar eddy current cover meters, which are being used for cover depth measurement. That's a performance criteria for the use of these tools. To go into a little bit more detail, and I apologize for those of you who may have seen this part of the presentation before. It's just a quick reiteration of theory before I go into some new content, is the principle of the eddy current cover meter. The transmitting coil receives an alternating current signal, which introduces an electromagnetic field, and that's transmitted in all directions around the cover meter. And if we bring a piece of reinforcing steel or any other piece of metal within range, it will induce from that electromagnetic field a matching alternating current flow of electricity, which produces its own electromagnetic field around the bar by turning off our transmitting coil and using a secondary receiving coil to measure the signal intensity of the induced electromagnetic field. We take our measurement. The key thing to understand here is at no point did our cover meter record a measurement in units of depth. It's recorded a measurement in units of signal strength. And it's this signal strength that we're going to use along with the calibration process to take depth measurement on site. So the best way to use a cover meter and to use it accurately and with confidence is to have a mental model of what we use it for and the particular tools that, and the particular things that will affect the measurement, but cannot themselves be measured. So I've got here an illustration of the actual calibration check block for a cover meter. Now, calibration is a process where we do two things. We compare performance to a standard. That's our check blocks here. And we may also adjust the internal settings of the cover meter so it can measure the test block accurately. Now, a supplier, they do the calibration process and they do it the same way every time to a manufacturer procedure. So measurements on this test block are 50, 30, 60, and 90 millimeters to a 16 mil bar. And that bar has a couple of key properties because cover meters effectively assume the length of the reinforcing bar is infinite. Now, there's no such thing as an infinite reinforcing bar. So we have a bar that extends well ahead and well behind the cover meter. The cover meter is lined up directly on top of that bar and parallel to it. And then the measurement is confirmed. The thing about a measurement is it's not a single moment of the number. So if you go and take out and look at your calibration certificate, you'll see that each measurement is taken 5 times. And they may be the same, or there may be 1 or 2 with a slightly different value. And what we consider our measurement to be is the average of those 5 values at each depth. And then there is the accuracy. So that is how close to the expected value we are. So we allow at 15 and 30 millimeters a plus or minus 1 millimeter difference at the moment of calibration. So that's how we achieve the presented accuracy under ideal circumstances. On similar 60 millimeter bar, we have a 1 millimeter change, and we allow 2 millimeters at 60 and 90 millimeter range. So if we don't meet any of those criteria, we'll adjust the device until it meets those criteria. And that is a fixed process. That is what the supplier or a manufacturer will do to confirm the machine is operating like all the other PM8000 cover meters in the expected window of performance. Now, there's you could buy a calibration block. It's not really necessary unless you'd like to run an internal calibration process using a traceable reference, because for a user, a verification and an adjustment is more useful job. So for use on site, it is much better to set up a proxy for your actual reinforcing layout as much as possible. So if this is new construction, this could be taking measurements off the reinforcing cage before casting the concrete. That's perfectly permissible. The surrounded concrete does not affect the measurement. So we could test performance and adjust settings of the device to make it match the required depth before casting the concrete. Or we could build a block analogous to our calibration block specific to what is needed on site. So if you're not using 60 mil bar, you're using 8 mil bar, you could actually build a small section of that reinforcing layout, making sure, just like on our calibration block, it goes well beyond, above and below the reinforcing layout. And then you can put all the real settings you'll be using on site into your cover meter, make sure it's reading correctly, and make the choice to adjust some of your neighboring rebar correction or bar diameter settings to give correct performance to your verification block. And it's much better that you have a documented procedure to adjust settings rather than because the calibration certificate just says it's working. Your verification says we are set up for precise measurement on our site. And adjustment is sort of this, and recording of any adjustments made is part of that process. The other situation, which comes up quite often, is cover depth measurements in existing structures. It might be working as a third party on new construction or using a cover meter for cover depth on existing structures. And in every situation, to provide the best accuracy, it's about confirming performance versus reality. And that means breaking out reinforcing. We are using a cover meter with a little bit of physical evidence to the broken out or where we have available proxy reinforcing layouts to achieve the best precision. So it comes out of the machine, out of the factory, performing and confirmed to be performing under its test. And then operation on site, it's about making the performance on site match. And that's a user documented process. So it's much better to build a block or set up or break out and investigate your real layouts. Now, that said, there's lots of tools we're going to talk about today that are going to make sure we're taking reasonable values of cover depth, and some of the new functions are very helpful there as well. So, continuing with our mental model, so the first thing is the other thing to stress is this adjustment is on a 60mm reinforcing bar. And if you build a proxy, that should be a reinforcing bar proxy. This is not a tool to locate post-tensioning. It's not a tool to locate other objects. The way that the conversion from signal strength to bar depth is calculated is built on bar depth. The references are all reinforcing bars. They're not other metallic reinforcing. So measurements to embedded railway, steel, post-tension tendons, anything obscure or esoteric, you'd have to at least build a proxy, and it'd be more of a pass-fail test than a direct measurement for those materials. I also do not suggest using a cover meter as a location tool for embedded objects in concrete. It is intended to measure and locate rebar close to the surface within that 100 to 180mm range where we're going to get some detection capability. It is not intended to replace ground penetrating radar for scanning before penetration or locating work. Now, the PM8000, at its heart, the way to get the best measurement is to isolate a single reinforcing bar underneath the active measurement range of the machine. And the active measurement point on our PM8000 is right on the center line of the LED indicators. We do have a screen. The screen provides input to the operator, but our electromagnetic coils, they are situated up and around the LED indicator. So when we're using the cover meter, we want to place the measurement point, which is the center line of the LED indicator, over top of and parallel, like I've got shown here, to reinforcing steel. This will measure the shallowest cover depth without interference. So the current illustration is ideal. But because it's producing an electromagnetic field all around the device, and that field will induce signal in any metal, we all need to be wary of other sources of signal. We won't be able to measure the depth of, but the machine would respond to areas like embedded cables, bits of tie wire, other pieces of metal that are embedded within that structure. Quite a common one, particularly at the deep measurement range of the cover meter, is metallic in-place formwork, which could produce a shallower measurement, additional metal close to the probe. And something which is very important to be aware of is your reinforcing is not continuous in your elements. If you're doing QA for new construction, you ideally want to be taking your measurements distant from any lapped or congested reinforcing. If you can't get away from congested, so closely spaced reinforcing, I'd say that's within 150 millimeters bar to bar positioning in longitudinal or latitudinal direction, you should be using the neighboring rebar correction. I will demonstrate the neighboring rebar correction setup in the video demonstrations. But lap reinforcing is a very common source of shallow measurements, which don't represent the real depth of the reinforcing bar. And I'll show a couple of ways to avoid that as we work. But the best way is to know it's there. So if it's new construction, you know your cage layout. You can choose the correct places to take your measurements from. And if you do need to measure in regions with lap reinforcing, you should be adjusting over a proxy of that reinforcing layout to get the correct values and be able to do a valid Q&A check. Because without adjustment, you will measure shallow on lapped reinforcing. We also just need to be conscious of other forms of interference. If you've got watches on, take them off. If your caps of your shoes are steel, keep them away from the measurement site. Just watch out for other signals. Don't run two cover meters in the same room. The electromagnetic field from one will talk to the other. So make sure that you're taking care to reduce sources of interference. And finally, it does need to be metallic reinforcing. If we've got something like a fiberglass or a carbon fiber reinforcing bar, that's not going to be detectable with a cover meter. It would need to be something, maybe a ground penetrating radar could provide position. And again, there's arguments about cover depth being a less important measurement for durability on non-metallic reinforcing. Now, the next two slides are going to be particularly relevant for bar depth versus bar diameter. So if we change the position of the bar, getting closer to the surface or moving further away from the surface, it produces a large change in the signal response. So if we've got our signal strength indicators turned on our PM8000, we're going to see a big change. But if we use a slightly different bar size, it's going to have a subtle change. So it can be harder to detect differences between bars. And it does mean that when we use that rebar diameter estimate function, it is an estimate. It is not the same way that the calibrated process is a cover depth measurement. It is a rebar diameter estimate. I would discourage anyone from using that as part of their structural calculations. The only way to know the exact size of the reinforcing bar is to expose the size. If we've got a relatively simple reinforcing layout and we understand enough to choose valid settings, we can get a pretty good cover depth measurement, but that bar size, it's not going to be precise enough to report to within one bar size, say. Now, your limitations of the tool. So you do have a range of about 150 to 180 millimeters. Do watch out for lapped reinforcing bars. I'll talk more about that during signal strength. If you are part of using a cover meter is knowing your reinforcing layout. So Dave, as you say, you're accessing existing structures. So part of finding places to measure is going to be using your cover meter or another tool to draw up a rough guide to your reinforcing layout. But I will show you the secondary tool we have for laps as well. And if the bars are close together, closer than 150 millimeter spacing bar to bar, do be using neighboring rebar correction functionalities. So the way the diameter estimates work, we measure in the standard and the deep range, the signal response, and look up what that would predict the bar size to be. It's an estimate, so watch out for that functionality. Now, so the critical thing when you're using your cover meter is to understand where the bars are before you take the cover depth numbers off the device, recording them with a spot or graphical data logging function, or simply taking your critical measurements for quality control. So if you don't understand where your bars are and you're using a cover meter, you cannot guarantee that you've got a precise measurement. So what are we going to do is we want to use the detection capability of our cover meter to sketch up the reinforcing layout before we begin. And the first bars we cross, there's two things we don't know about them. We don't know if we are moving the probe on top of a bar that is parallel to its path of travel. And we also don't know if we are on the bars closest to the surface or the reinforcing bars that are sitting in contact and beneath the bars closest to the surface. So we're going to discard anything but the position on the first passes of our cover meter. On the second path, we can take the measurement point of our cover meter. Again, that is lined up with the LED indicators on the PM8000, and we're going to pass that in between the parallel reinforcing bars. So we now know enough that the number we're recording should be a valid measurement at the shallowest depth. So we can take that number and we can check the depth of the bars perpendicular to those, and we can take the closest cover depth. That's our critical measurement. And we're not going to take a single measurement ideally. It is much more appropriate to use the cover meter to take an average and consider the average cover depth. But there are operation modes like the minimum bar depth, which we can use to do a bar by bar check of compliance as well. So what we're particularly trying to do is we're trying to eliminate the situations we can see on the bottom, which is lapped reinforcing bars and moving the cover meter with a bar underneath its measurement range, in front of the bar we're trying to measure to. The bars get a little close together, like in the top right corner here. That's fine. We can use neighboring rebar correction. So on a simple reinforcing layout, that's not too difficult. We can just use the process we've shown there. You do need to be conscious of angled bars. So that's why the marking up can be helpful. It will help pick up if bars don't line up completely clean. And this is also where we're going to be able to take the position values for correction factors. On more congested layouts, you do end up needing to know the layout as much as possible. But what we can do with the new signal strength behaviors, if we want to get away, if we want to move away from understanding our clear regions, we could do, for example, look at signal intensity. So I'm going to use a scale between green and red here. And let's say I'm passing my probe in this direction. So I'm going to, and all of the bars are at the same depth. These measurements for this bar, this diameter, would be the lowest signal. Then, because we have not corrected for neighboring rebar, there's going to be increased signal intensity here. Quite a bit, I apologize, quite a bit stronger in these lapped reinforcing regions. That's probably going to be our highest signal. And back to a moderate increase there and a more modest value here. And now we need to think about what that means. If we have no reason to believe that the reinforcing cover depths have substantially changed, we should only see a modest change in the signal intensity. So if we were using the operation mode of a line scan, this chart I'm drawing represents signal intensity. It would end up looking something like this, where we have more intense signals in our lapped region, and then weaker signals in the single bars, and there will be a medium intensity signal where bars are close together. So the first point of information we have looking at this is we know regions where if we want to measure correctly, we would want to measure the reinforcing spacing and use neighboring rebar correction. That would lower the apparent depths of these two situations. This is a fairly predictable measurement and it should be close to things. Now, but you will sometimes see this relationship. There's two reasons you might see this. One would be if the bars I've highlighted are larger, or if there is a spliced bar in this position. So if we've got a expected cover depth and expected signal intensity, which there should be a small change, maybe going from 50 mils to 48 mils cover or 40 mils cover as the reinforcing changes slowly over a region. If we had a predictable large signal strength increase, we would need to question whether we found lapped reinforcing bars, and that might trigger places to either discount, because in this case we could get up here and take the same measurement. So if I take my measurement in this line, I would have a similar chart, but because we are away from the lapped reinforcing, the main excessively strong signals would come from the close spacings. So that's a sign that we've got up and away from those lapped bars. I'll show you the signal strength indicator during the video demonstration, but these are the ways you need to think about in complex situations, either looking at signal intensity or considering what more we can, or considering if we can get some information about the reinforcing layout before we begin. Honestly, in a complex layout like this, if you start getting complex responses, it may be appropriate to bring in a tool like ground penetrating radar to find single reinforcing bars isolated from the other bars to pick good places to measure cover depth. And we could even adjust the depth precision of a ground penetrating radar based upon that. Okay. So that's the conclusion of the content on cover meter operation. I'm going to go to demonstrating PM8000 functions in a second, but before I do, any quick questions on the operation or the content I've just presented before I keep going? Could you provide an example of proxy measurement on an existing structure to verify operation? So look, with proxy measurement on an existing structure, you've got a problem, which is your prototype is your structure. You don't have a easy ability to build a proxy, so you do need to turn towards destructive testing in most cases on existing structures. If you had something like a drawing or a layout, even something which you're not quite sure of, you could build up a proxy from that. But without information, you are limited, and there should be some element of physically looking at the bar conditions that are there. If you are having to make a choice without breakout, there's approaches you can take using your knowledge of how structures of that age, of that type would be constructed, but you are going to have an inherent lack of exact measurement without knowing the full story. So David asks, would the results be affected if the slab is supported by steel beams? Absolutely, it could be. Now, we do have the standard and deep operation modes for a cover meter. So if we're looking at the standard range, that's a weaker signal. So maybe if you're on a 150 millimeter reinforcing 150 millimeter slab measuring cover in standard mode, the effect would be fairly insignificant. But if you're in deep range, it could definitely have an effect. Now, Sean AK asks, is this a contact method? No, the cover meter measurements are not a contact measurement. So we don't need to hold our probe in contact with the face of the concrete to measure. We can even see if we're using the wheeled car, there's a small gap underneath it that's insignificant for measurement, and it's removed in the data logging modes that use the car. So it's actually entirely appropriate if you've got a rough surface to measure the size of and place a board or something to roll the top of or slide a top of when you're measuring. It simply responds to the presence of metal. It doesn't matter if it's moving through air before doing so. The only source of interference is other metallic conductive metals. The short rebar in the PM8000 case, that's purely a functional check. So we talk about the user verifiers. One of the simplest verifications you can do is, if I put it on top of the cut of the bar with the settings I always put in, do I get the same number, or is it wandering? It's not at the level of a calibration check, but it's a performance check. Does it turn on? Can it find the bar cleanly? And are the numbers coming out with the same settings I used before, the same as they were? So it's just a quick performance check. Is it therefore acceptable to verify the cover is operating correctly by utilizing a calibration block with known covers prior to executing grid scans? So if you're doing grid scans, yes, doing your verification on a block with known cover will let you know your machine can measure correctly. But what's more important with grid scans is actually avoiding your parallel bars. So whenever you're doing a grid scan, you need to already know your grid layout, ideally have it sketched up on the surface, or at least the path you'll be rolling your cover meter through to get really good, accurate cover depth for the top longitudinal and the lower latitudinal bars. Now, the new multi-line scan function, which is in the PM8000 Pros, is only a single, but is intended to reduce some of this complexity because it's now collecting essentially a chart of cover by cell, which is good for comparing to measurements like half cell potential. I'll demonstrate that. How accurate is it with concrete reinforced pipe? No problems using for reinforcing inside concrete pipe. You do need to be conscious of the curvature. But it's a minor effect. And Mohammed has asked about if the reinforcing steel has corroded, will the results be accurate? If you've got substantial section loss, it would affect the signal you receive, but it's very hard to characterize exactly the effect. If you get the kind of section loss that would occur if it's expansive corrosion, would probably damage the structure before it's the main change on your cover depth. So yes, it's another source of uncertainty, but it's probably going to do bad things to the structure well before it's affecting cover meter signals. Though I'm aware that things like black rust, non-expansive corrosion do exist and are worthwhile being conscious of. I'm going to keep going because I want to get across to some of the demonstrations of the new functionality. Now, these are pre-recorded videos I'm going to speak over. I can pause and I can go back if I need to. And I'll still be keeping an eye on the chat as best I can as I go through these. So, firstly, this is PM8000 Lite, or using the PM8000 and PM8000 Pro without its scan car. When we turn it on, just power button, top left on the face of the device, it's going to want to be zeroed. Zeroed is telling it what no metallic signal is, and that needs to be taken off and held up in the air away from all metal. Then the right-hand button is pressed, and it will zero, and then go into the default locate measurement mode. So the locate mode measurement mode is intended to find the center of reinforcing bars and provide an accurate cover depth at that position. It's also able to indicate the position in between bars if they're sufficiently close together. So the Profimeter is a dual coil cover meter. So there is a sending and receiving coil, transmitting and receiving coil on the left and the right-hand side of the probe. So the reason that the device can provide LED indicators, and also I'd like you to watch as this video plays, this little white dot move left and right on the screen, because that's the other indicator of bar position. When that small dot is moving opposite the direction the cover meter is being slid, you are approaching the center of a bar. when that small dot is moving in the same direction, you're approaching a midpoint. So let's see how that looks. So if I slide this cover meter out to the right, the white dot moves, is moving in the same direction. So I'm approaching a midpoint. Same as I come back to the left, that dot is indicating we're approaching a midpoint. But as we get closer to the reinforcing bar visible at the bottom of the screen here, you can see that the green arrow points left, the white dot begins to come towards us, and then the device indicates center of bar and 30 mm depth. At that point, we could press the right-hand side button, just a tap, to estimate bar diameter. You can't read that. That was a 20 mm measurement in this position. And then it will slide along and indicate the position of the next bar. We're going past the midpoint here, so the dot is moving in the same direction as we're pushing. Then it comes back opposite our push as we center on the second bar and take the second depth and diameter estimate. Now, this is not a data logging mode. This is just the locate mode. So none of these values are saved. They're just being presented to the operator as he works. We don't want, just quickly to go back on that, what just happened on the screen there. We don't want to take a cover meter up and place it on a surface and read the cover depth. That is not the correct procedure. We want to be sliding it across the bars in contact with the surface, because that will allow the location process to operate correctly and you to find the center of the bar, the shallowest cover, the cover depth measurement. Now, Danny, I do see a question about when you calibrate on 60 mm bars, you measure cover for a 6 mm bar to what accuracy? So the calibration is do you mean specifically the calibration done by the manufacturer, or do you mean the a verification check done by the operator? Because if it's the manufacturer, the reason we use a 60 mm bar is to confirm, is machine A correct to machine B, correct to machine B, and to C, and are all of them able to measure a controlled measurement the same way? Because all of the other parts of that device, the internal calculations that give correct cover depth for 6 mm bar or 40 mm bar when measured normally, all of that is done by the manufacturer. They've built the calculation that goes, we have a 6 mm bar with say the signal strength is 5,000, so 6 mm bar, 5,000 arbitrary unit signal strength means 20 mm cover. That's the manufacturer's development of that device, and that measurement will be accurate. But to make sure that the cover meter you own works correctly, we have a calibration process. So we're not testing every possible reinforcing bar diameter at every possible depth. That's done as part of the product development. What the calibration does is take a typical situation and confirming that a cover meter with identical settings as every other cover meter checked measures correctly at your 90, 60, 30, 15 depth. And then we have 2 points of information. The machine is developed to be accurate at 6 mm bar diameter over its full depth measurement range, and the particular device in your hand has passed the same test as every other device produced, which confirms it is operating the same way. So development made sure we're accurate across all bar sizes and bar depth ranges, and calibration confirms that the particular device you're holding is working the way the manufacturer intends. It is to specification. Then, if you're particularly concerned with getting the best possible measurement of 6 mm bar on site, that's why you can do a verification. You can locate bars, measure cover depth, drill down and have a look. And it should be bang on. And if it's not, You're then able to adjust the settings. In the PM8000, PM8000 Pro, you could use a small cover offset, or you could essentially tell it, no, it's not, we're measuring to a 6 millimeter bar, but we're performing better with an 8 millimeter bar setting. So make that adjustment. So in critical jobs on the QA or on existing structures, that verification process to a sample and an adjustment of the settings of the device to make it provide real numbers versus a physical reference that you control is a secondary step, and it's a different part of the quality of measurements process. So the calibration means the machine is the same as all other machines. The development of the machine means the machine is able to measure accurately. And then your verification and checks on site are what you do if you need full confidence that today's measurement is valid and useful. If you look at some of the processes used by coding inspectors, by people in metal ultrasound, a lot of their process is to use test blocks or proxies to adjust the settings of their devices to measure as precisely as they can. It's the same thing with the use of a cover meter. The more critical the measurements, the more important it is to have an understanding of how it's behaving today. Okay, I'm going to keep going on with the video content, so I do want to try and get through as much as I can before 1 o'clock. So the next functionality I want to demonstrate is the data logging functionality. In this case, we're going to go, I apologize. Now I'm going to quickly go through the so we have the bar. We can change our bar diameter setting with the diameter options. That's where we put that in. That's the setting that we're discussing. And then we can choose one of the data logging functions. So we've got a spot scan auto or spot scan manual. I'll be demonstrating both of those. So this is going to be the spot scan manual operation. In this mode, we move, if we press the button here, we see that it's presenting statistical information of the measurement. So now I can move my cover meter and line it up on top of a reinforcing bar. And by pressing the right button, just to tap, we can estimate the diameter. And then the left button, just to tap, we record both numbers. So I've recorded 30 mil depth and the diameter measurement. I will line up on the second bar and I'll do the same process. Each time, estimate diameter, and then record depth and diameter as part of the manual spot data logging mode. Take a few more of those. I'll just quickly let that slide past as I collect my additional measurements. And when I've concluded that, I'll be able to load these onto an iPad and see the outcome of that measurement. Now, I do have an automatic function too. So if I go back into my settings and I turn on the spot scan auto, what I'll be able to do now is move the cover meter over a bar and it will automatically record the cover depth. So each time I pass on the bar, it will count up. So count 1, 30 millimeter diameter, count 2, sorry, 30 millimeter depth, I apologize, count 36 millimeter depth, and then each time I cross, it will take that measurement as well. So this is an automatic mode. If I do line up and press the diameter, it will record as that as well. And either of these measurements can now be loaded up inside the iPad application. So connect with Bluetooth. I'm going to make a new folder and put these spot scan measurements in. And it will then download and import the data from the device. And if we open those up, we're going to get a record of bar depth, bar diameter estimate, and we can adjust that visually to show compliance with required cover depths. So each of these measurements, we've got the measurements of the lowest and highest, the average value, the standard deviation, and in the measurement where we've taken the diameter estimates, those are also visible, and we can see the lowest and highest diameter as part of those recordings as well. So that's the main data logging functionality. Okay, so firstly, this one, this is showing the functionality of the minimum bar depth. So we can tell it we need to have a 30 millimeter bar depth in this case, if a bar depth of 40 millimeters. And when we line up, it will blink and provide an audio indicator the cover depth is not sufficient. So if I increase the cover, put a block in place, we're now at 39, we're still not compliant, go a little bit higher, and now I'm compliant and I get a solid indicator for the minimum cover. So that's minimum cover measurement. This functionality is about the deep measurement range. So we normally operate in a standard measurement range, which ranges down to 80 millimeters maximum. If we wish to use the full 180 millimeter range of the device, and I've just put a block on top of my my test block here to make everything deeper, I'm now measuring at 66, and if I go a little bit higher than that, I'll end up measuring up above the 80 mark. So this is going to be the deep measurement mode you'll use to measure cover above 80 millimeters. If you don't want to use this unless you have to, you can no longer estimate bar diameter below around a 50 millimeter depth. And the additional electromagnetic field makes this measurement mode more prone to interference. So now we're going to go across to the diameter settings. So back to standard range. And because I'm going to be working over mesh, I'm going to enter 6 millimeter bar diameter in 2 directions. And I'm also going to be putting a spacing measured of 100 mils between bars. So with those 2 measurements, I'm going to see the behavior available with these corrections. So 6 mils for each bar, 100 millimeter spacings, centers entered. And now we're in a bit of a tricky spot because the cover depth here is reasonably deep for bars so close together, which are so small. So I'm going to be able to record a valid cover depth measurement, but I may not be able to easily locate the position of the bar. So as I move this round, my location is going to be weaker. I'm having trouble snapping onto the center of the bars because they're so close together. But I can still look for local minimum cover depth because I've got my correction factors in and take off useful cover measurements for this situation. You see, there's not much variation on the cover depth numbers as I slide across the bars. So the depth precision is retained even after we lose our ability to locate individual bars, but you will need to use your neighboring rebar correction in both directions to take measurements like this. The other advantage of this is because we can use a large bar in one direction and a small bar in another, things like the ties in piles where it's a fairly thin bar around a very substantial bar, we can account for that large vertical bar when measuring the closer ties. Okay. So that's what the neighboring rebar correction function is. So the final function I want to show for the PM8000 light operation is the new signal strength modes. And these are very useful where you've got complex layouts. So I showed you what we can do if we're in a line scan by sketching out the functionality. The signal strength bars, so we've got one on the left and one on the right, allow for similar operation where we don't have a line scan behavior. So this is showing the direct output of left coil and right coil. So as I approach a bar, left coil increases first. And then as I center on the bar, both of our coils are up and our normal centering behavior is shown. And then as I go to the midpoint, left coil drops, then left coil increases and right coil drops, and then we recenter on the middle. So we can actually see the input to the machine in detail with the signal strength bars. And we can tell them what a typical value is. So this is particularly useful with a layout here, because I will be able to what I can do with this is I can set it. So if I center on a bar and I hold the left-hand button for 2 seconds, it will reset the intensity of our signal strength bars, which allows me to distinguish whether the intensity is the same or different. So if I had a lapped bar, the intensity would be substantially greater. In this test block, the left bar is a smaller bar than the right bar. So I can see the weaker signal on the left bar versus the right bar. And now I can see a stronger signal on the right bar and a weaker signal on the left. So that's the signal strength functionality. So those are all of the new behaviors available in the PM8000 Lite cover meter. If you're an existing owner, all of this functionality is available in the new firmware version. The final thing I'd like to demonstrate is the line scan functionality. And I do apologize if people need to start leaving. I do understand we've just made it to 1 o'clock. So line scan functionality requires us to install. Hi, Michael. Yes, so the moving dot was always available, but it's now on by default. If you upgrade your firmware version, that'll become available. So just follow the procedure. It'll be in the email we distribute to upgrade to version 1.2.7, and you'll receive the dot and also the ability to turn on the signal strength bars. So I've connected to my iPad, and I'm zeroing out with the probe inside its scan car, the wheeled cart. So now I can start using the line scan and the multi-line scan functions. So to demonstrate the line scan function, if you haven't seen it before, we roll to the right, always to the right, and we will measure the depth of bar, and we'll see a signal strength readout. So our settings, we can choose standard or deep. We'll stay in standard. We do have other units, but we'll stay with metric. And with the PM8000, PM8000 Pro, we can do a cover offset. So if we've got like a carpet layer or some sort of other surface before the concrete cover itself, we could offset the cover if we'd like to do so. We do have the same settings for rebar diameter. So what I could do here is if I wanted to, I could very quickly put in that same 6mm, 6mm, 100mm bar spacings, 10 centimeters in this case, if I wanted to do so. So that's another way to use neighboring rebar correction. But once I've turned all that off, just back to 80mm, which is the size of the smaller bar here, and I'll start my measurement and I'll roll my cover meter across. The yellow line is signal intensity in this view. So we can see on the bigger bar, close to the surface, we've got a stronger signal and a more apparently shallow bar. So smaller bar, a little bit deeper, 36. Larger bar, a bit more shallow, 31. And we're just collecting those measurements a few times, so I've got something to talk about. Now, once I've completed my measurements, I'll be able to stop. Now, I'll be able to stop that if I wanted to. Now, look in the bottom right corner for me, please. That green box that varies to red and starts to move around, that is a coil balance box. If I'm too close to a bar above or below the path I am rolling, that bar will go red and it will move towards the position of that bar. So pulling the cover meter back towards yourself until you are centered in the middle of the top, higher and lower bar, and then can roll over the bars you're perpendicular to, will ensure precision in your measurements. So do be aware that you have a visual representation of coil balance, so top and bottom balance, in the PM8000 and PM8000 Pro configurations. I've stopped my measurements now, and I just want to show a couple of the editing functions we have. If we hold down on a bar, I can delete measurements I don't want. So when I demonstrated the coil balance, I created an artificial response. So we're going to exclude the artificial bar from the measurements. And on all of the more shallow bars, they're not the 18, they're the 21mm diameter bars. So I can individually set them, change the diameter to the real bar diameter, and we can see that they gained a millimeter of cover depth from that adjustment. So they got a little bit more deep because the machine took into account the change in bar diameter. This is great for more complex layouts where you've got bars of different sizes close together, and you know you do. Finally, I've changed into a simple mode where my left-hand scale is now your cover depth, which is great for presenting results. But the people who you are providing your results to, they don't need to see signal strength. They just need to see pass or fail. Here is the bars along that line. So that's the line scan functionality and the new behaviors and editing modes we have available. Now, because this is on the iPad, we can also record information like a photo of our test area on Workspace. And Workspace is the cloud service that the PM8000 and PM8000 Pro users will be able to collect their measurements from. So you don't need to stay on the iPad. You can go straight to your computer and see your results on your computer. I'll show you that when we're done. There, Michael, there is no corresponding Android app. The Screening Eagle Technology devices are a iPad-only application. You can use the PM8000 Lite without the iPad, but if you'd like to collect your data logging results, you'll need an iPad to connect to do so. So the final measurement mode I want to demonstrate here is your multi-line scan. So this is a new measurement mode, which looks a lot like the area scan mode you may have seen before, but the difference now is we are only going to collect bars in one direction. So just like with an area scan, we should already know our reinforcing layout and already know which bars are closer to the surface. Once we've got that, we set up a measurement grid, but the measurement grid is really setting up measurement cells. So it'll make sense at the end, but if we tell it we've got 100 by 200 millimeter spacings, we're going to get a 100 by 200 millimeter grid on which we record those values. And then we'll collect the values the same way. So I collect 4 lines of measurement. So you can see here, each time I pass, I'm collecting another line of data. And when I finish up, I can turn on my heat map display. And now I see the closest bar, that I see the shallowest cover in that cell. And if I choose to, I can just make it a little bit transparent. We can see the bars that signal came from. I've got an align rebar position option that just makes everything line up a bit more tidily. And now this is useful because this is the shallowest cover in each region. And if we're doing something like half cell potential measurements using the PM8500 half cell potential meter, its data is very much the same. So corrosion potentials, and now we can export our cover depth values in the same data format as our corrosion potentials. Very useful for comparative work. If you're an existing PM8000 owner or PM8000 Pro owner, sorry, if you're an existing PM8000 Pro owner, this multi-line scan functionality is already available for you with the latest version of the iPad application. Final thing to view is I'm just going to show you quickly Workspace. So something people don't always know that is available for the iPad applications is access to Screening Eagle's Workspace website. So it is workspace.screeningeagle.com, and you log in with the same account as you use in your iPad application. And this is for ground penetrating radar, Schmidt hammers, cover meters. Any of the latest generation of Screening Eagle technology devices will have access to Workspace as part of its creation. And so all of the data that I've been taking today, my multi-line scan, is already ready with logbooks and data outputs, everything I might want to use, and the ability to do my exports as well. So if I'd like to export that to an Excel file, I can export from the website. I know it's all available here. So we can see for each line scan, we have the depth carried, spacing between it, everything we need to make use of that data available. So that's the completion of today's presentation. We've seen the new behaviors for the PM8000 Lite, the additional PM8000 Pro multi-line function, and we've done a bit of a review of our cover meter theory and cover meter operation. And I presented a bit of a mental model of how to think about a cover meter. And really, that's the most important thing from today. If you consider your cover meter to be a rebar-focused tool, and it is sensitive to the presence of metal, which means that's also its source of interference, you will be able to make better choices.